Do aliens exist? There are few questions of more profound importance when it comes to our place in the universe. But while the majority of people believe alien life is out there, it's a lot harder to pinpoint exactly where. At least that was the case until we started looking at the TRAPPIST-1 Star system. In the hunt for alien life, there are few better candidates. We know that Earth-like planets are fertile ground for life. After all, life arose here. So to find a planetary system that is seemingly full of Earth-like planets and is relatively close by, it's no wonder that scientists are interested. Those researchers have now turned humanity's most powerful space telescope on the TRAPPIST-1 system. So it's time to find out the truth. Has Webb confirmed that the planets of the TRAPPIST-1 system are conducive to life? Or is it back to the drawing board? I'm Alex McColgan and you're watching Astrum. And together in this supercut, we will go through every planet in the TRAPPIST system and see why new data is narrowing down the most likely places life could arise. Evaluating a star system for compatibility with life is tricky. Although much of it is about the planets themselves, a large portion of the conditions depend on the star they're orbiting. So let's begin at the heart of the TRAPPIST system, TRAPPIST-1 itself. The ultra-cool red dwarf star, a star which is just a little bit bigger than Jupiter, but a lot more massive. Red dwarf stars are the most common type of star in the galaxy. Even our closest neighbor, Proxima Centauri, is a red dwarf, as are 50 of the closest 60 stars to us. Being so cool means they are very long-lived. Stellar models suggest they could exist for trillions of years, which is far more than the current age of the universe. Although there are many known red dwarfs with exoplanets around them, typically red dwarfs are dubious candidates to have life. This is because the Goldilocks zone, or the distance from the star where water could theoretically pool on the planet's surface, is extremely close to the parent star, meaning any exoplanets orbiting in this zone are likely tidally locked. This means one side to the planet would always be facing the star, and the other side would be in perpetual night. And the night side would be cold enough for gases in the atmosphere to freeze. Also, red dwarf stars are often flare stars, or stars that can have their brightness increase very rapidly to magnitudes brighter than they are normally. This is similar in a way to a solar flare on our sun, but on a much grander scale. This variation in temperatures and radiation is not good for life to develop on any planets nearby, or for planets retaining their atmospheres during a huge flare. TRAPPIST-1, however, while being a red dwarf, does not flare up as much as its other red dwarf cousins, 30 times less than a typical red dwarf star. Great for the chances that atmospheres exist on the exoplanets around the star. Although the star was first discovered in 1999, its full planetary lineup wasn't revealed until 2017, when it became the first and only planetary system to be discovered by the TRAPPIST Optical Robotic Telescope. This telescope is made up of two parts, TRAPPIST South in the Chilean mountains and TRAPPIST North in Morocco's Atlas Mountains. They use transit photometry, a technique that measures periodic changes in the brightness of a star to find orbiting planets. In other words, if a planet passes between us and the star, then some of its light is blocked, and so we detect a dip in the star's apparent output. By taking multiple observations, the telescopes were able to isolate the individual orbits of multiple planets around TRAPPIST-1. Initially, their data analysis only found the 3 innermost planets, but further data from both of the TRAPPIST telescopes, as well as the Spitzer infrared space telescope, took this total to 7. And not only that, but they are all rocky, and all, at least roughly, Earth-sized, making this the most Earth-like planets found around any star. But with such a small, dim star at the center, is there really any hope that they could be habitable? Let's now talk about the planets of TRAPPIST-1. It should be noted that our current observations aren't going to be perfect, and will only improve as time goes on. But this is what we think at this point in time. Optimistically speaking, 6 of the 7 planets within TRAPPIST-1 orbit within the system's Goldilocks zone. These planets are so close together, the furthest out planet still only orbits at roughly 9 million kilometers away from the star. In comparison, Mercury orbits our star at 58 million kilometers. TRAPPIST-1b is the closest planet to the star, and it orbits its star quickly. A year on TRAPPIST-1b lasts only 36 hours. It's slightly larger than Earth, but with the same mass, meaning surface gravity would be about 80% of Earth's, quite similar to Venus. It was initially thought that, like Venus, it also had an extremely thick atmosphere, potentially full of CO2, meaning that because this planet only orbits 1.7 million kilometers from the star, it would have been really hot. However, new data from the James Webb Space Telescope might have revised our opinions. The James Webb Space Telescope is one of the most powerful and sensitive telescopes to date, and the teams who were involved with developing the telescope were rewarded with guaranteed observation time. One group, the Deep Reconnaissance of Exoplanet Atmospheres through Multi-Instrument Spectroscopy, that's right, the DREAMS team, immediately wanted to set James Webb's sights on the TRAPPIST-1 system. The James Webb Space Telescope is uniquely sensitive and precise, so much so that it can detect spectral signatures from the thin band of gas that makes up the atmospheres of these planets, a whole 40 light years from our own. It does this thanks to a technique called transmission spectroscopy. As an exoplanet passes its mother star, James Webb not only measures the drop in brightness, but also how the spectrum of light changes. The telescope's near-infrared spectrometer, or NIRSpec for short, measures the wavelengths of infrared radiation closest to the visible spectrum. Molecular bonds absorb energy in this range, and different bonds, like this carbon-hydrogen bond in methane, or this carbon-oxygen double bond in carbon dioxide, absorb different wavelengths. It means that by measuring which wavelengths are absorbed as a planet transits its star, we can first of all work out if there is an atmosphere, and then, if so, determine which gases are present. And it's been particularly easy to get a read at TRAPPIST-1. In fact, the data we have is 10 times more sensitive than what we have on any other system. Why? Counterintuitively, it's because the star is relatively dim. The light a planet obscures causes a bigger relative drop in apparent brightness of this star than the same planet passing in front of a large, bright star. A bigger difference is easier to measure. With the help of the Webb data, spotting atmospheres in the TRAPPIST-1 system felt less like a slog and more like a game, with scientists spending time every day trying to crack the code on which planets could be habitable, and I bet they had fun with it. But if you're looking to have fun while cracking code, you should check out the sponsor of today's video, Coddy. Coddy is all about making learning to code fun, helping you to build a lasting habit of learning. They give you challenges, quizzes, and real-world projects to help you build up your coding skills through doing, no matter your starting point. It's easy to get into. Coddy starts by asking you a few questions to tailor your journey, and then you're off. Build your streak through daily bite-sized lessons, and if you ever get stuck, there's a helpful AI tutor that can offer instant feedback. The best part is their content is free. Do up to 5 lessons a day with no cap on how many times you can retry a lesson if you're wrong. Or, for just $4.99 a month, you can get truly unlimited code runs to keep you coming back for more. And with that pricing, why not give Coddy a try? Start building up your streak by scanning my QR code or clicking the link in the description below to see what Coddy can do for you. Speaking of seeing, let's go back to what the Webb saw on TRAPPIST-1b. Thanks to the James Webb Space Telescope, it has been revealed that TRAPPIST-1b is much cooler than it had been predicted. Surface temperatures on its sunward side only reached 227 degrees Celsius, which essentially rules out any significant atmosphere. there is no chance of life on this bare rock. But what of the other planets? TRAPPIST-1c is the next planet, orbiting at 2.4 million kilometers away from the star. Its year lasts 58 hours. At this distance out, it is getting about 2 times the starlight Earth gets from our Sun. Its size and mass are about 10% more than Earth, which means it has a very similar gravity to Earth. It is very similar to TRAPPIST-1b in that scientists initially believed it to also have a thick water vapor atmosphere. However, once again, the James Webb Space Telescope revealed a much cooler surface temperature than expected. Interestingly, the coolest rocky exoplanet ever categorized based on thermal readings. This means that, once again, there is either no atmosphere on TRAPPIST-1c or a carbon dioxide atmosphere that's even thinner than the one on Mars with no clouds. So it's likely that TRAPPIST-1c was formed with little water, as otherwise some might have become water vapor in the atmosphere at these temperatures, and scientists don't see any. Next is TRAPPIST-1d, only an extra 1 million kilometers further out than TRAPPIST-1c. 1 year lasts only 97 hours. TRAPPIST-1d is kind of like a mix between Earth and Mars, as it is 30% smaller than Earth and only 30% as massive, meaning the surface gravity is little under half of Earth's. It is found on the inner part of the Goldilocks zone, meaning at this point in the star system, the surface temperature is now cool enough for water to pool on the surface. It only receives 4.3% more starlight than Earth, and combine this with stellar flares from the star, it is likely to still be pretty toasty for our standards. According to the James Webb Space Telescope data, TRAPPIST-1d does not have an Earth-like atmosphere. No water, methane, or carbon dioxide have so far been detected. But this does not rule all possible atmospheres out. There are some indications that TRAPPIST-1d could have a volatile layer on the surface, perhaps an ocean, hidden beneath a thick, obscuring atmosphere that could be throwing off Webb's readings. And this is where oceans and atmospheres become very important, because as I mentioned, all these planets are tidally locked, meaning a thin atmosphere or no atmosphere means that one side of the planet could be scorched and the other side would be freezing, much like what happens with Mercury. Venus, on the other hand, has a thick atmosphere which circulates the heat around the planet, meaning day or night, the temperature is the same. So if TRAPPIST-1d has only a thin atmosphere or small ocean, the chances are that one side of the planet would be devoid of anything but rock, the other side might be covered in ices. There might be a small band of habitability along the twilight zone, but that would be it. With a large ocean or atmosphere, the planet might be able to distribute the heat much better, meaning it could be habitable all over, as much as we understand habitability anyway. This planet may well be an ocean world, with over 250 times the amount of water more than Earth's oceans, although other studies have suggested the atmosphere could be more similar to Venus's. Conversely, there could be no atmosphere there at all. The JWST has not been able to rule this one out either way. Next, let's take a look at TRAPPIST-1F. From TRAPPIST-1F and beyond, we are still in the Goldilocks zone, but it is starting to get much cooler at this distance. TRAPPIST-1F orbits a distance of 5.8 million kilometers from the star, and a year takes 220 hours, or roughly 9 days. Its size is very Earth-like, although it is less dense, meaning surface gravity would be about 80% of Earth's. The most recent studies on this planet have suggested that its low density means it is likely to be 20% water, which at this distance from the star would cause a massive greenhouse effect, meaning the water would be in gaseous form. This is known as a steam world, and would probably be no more habitable than the ice or gas giants of our solar system due to the high pressure and temperature on the surface, likely in the hundreds of degrees Celsius. TRAPPIST-1g is slightly bigger than Earth and orbits at 7 million kilometers, taking 12 days to do so. There hasn't been too much information discovered about this planet, other than water has again been found on it. This planet is still found in the Goldilocks zone, although right on the far edge, so it is still a candidate for habitability. And lastly, TRAPPIST-1H. It orbits at 9.3 million kilometers and takes 19 days to do so. It's the smallest of the known exoplanets in this system, and also the least dense, meaning its gravity is comparable to our moon's. Due to the cool nature of the host star, being this far out means the planet is likely icy, as it does have water. Theoretically, it could also have liquid water on the surface if it had a hydrogen-rich atmosphere to act as a greenhouse gas, but again, little is known about this planet. So, we've reached the edge of the TRAPPIST-1 system. Could the system really be habitable? Well, it depends on a number of factors. But while some of these exoplanet candidates are unlikely, others so far remain promising. Water has been detected on some. The host star is a red dwarf, but not a very active one. If these exoplanets have strong enough magnetic fields, they could deflect a lot of the solar wind. They are also all roughly Earth-sized with similar gravities and densities. Not a huge factor for life, but we know it worked here. And lastly, although these planets are tidally locked, they may still have mechanisms for evenly distributing the heat across the planet. But you might have noticed earlier that I missed a letter. I went straight from TRAPPIST-1D to F. That is because I saved our best candidate for a life-supporting planet until last, TRAPPIST-1e. TRAPPIST-1e orbits only 1/13 of Mercury's orbit, which means its orbital distance is right in the middle of the predicted habitable zone, where it receives about 2/3 of the energy that we do from our Sun. And that is why scientists are so curious about this planet. Using James Webb Space Telescope measurements, the team have already discounted TRAPPIST-1c and D from having atmospheres. But the results from observations of TRAPPIST-1e, a rocky planet around 0.9 times the size of Earth, were so intriguing that scientists couldn't ignore them. It looked like this planet may, in fact, have an atmosphere, and that was more than enough evidence for the DREAMS team to decide to use up all their guaranteed James Webb time trying to find more. So far, they've seen 4 TRAPPIST-1e transits with James Webb. But what did they find? Well, we can start by discounting a few possibilities. We now know that TRAPPIST-1e does not have a primordial atmosphere, one a planet is born with. These are usually dominated by light gases like helium and hydrogen, which haven't been detected. They were likely stripped away by the star's radiation early on in its life. Nor does it seem to have a carbon dioxide dominant atmosphere like Venus, which is thick and dense. An atmosphere like that of Mars, which is thin and sparse, is also unlikely given the recent measurements. Believe it or not, all of this is good news, as it's unlikely that any of these atmospheres could support life. Well, not as we know it anyway. So what atmosphere does it have? Well, here's the big one. There could be an Earth-like atmosphere, one dominated by a heavier gas such as nitrogen, with a strong greenhouse effect from water, carbon dioxide, or methane. Such an atmosphere with a surface pressure of around 1 bar, equivalent to Earth's, may be able to sustain enough heat transfer to the dark side of the planet to allow a global surface ocean, despite it being tidally locked. Were this confirmed, that would make headlines the world over. However, that might be too much to ask. The data instead slightly favors the idea that TRAPPIST-1e is a cold planet without a global ocean. Instead, high levels of methane could be creating a reverse greenhouse effect. TRAPPIST-1 has a surface temperature of about 2,300 degrees Celsius, much cooler than our Sun's 5,500 degrees Celsius, and more of the energy it outputs is shifted to the near-infrared wavelengths. Atmospheric methane can absorb that energy before it even reaches the surface of the planet, then re-emit it into space, resulting in a cooler atmosphere. For the tidally locked TRAPPIST-1e, This would mean that liquid water may only exist on the surface of the planet that permanently faces the star. No global ocean here. But that's not necessarily bad news for life either. Such conditions could satisfy Darwin's warm little pond hypothesis of the origin of life, and atmospheric modeling has backed this up. Simulations suggest that even if TRAPPIST-1e has limited water, or if what water there is locked on the dark side of the planet, it could still have a stable atmosphere. Although, this may lead to what's known as Terminator habitability, where life could only find a home across a dynamic band in perpetual twilight that separates day from night. But water on the surface isn't the only option. We know TRAPPIST-1e is rocky, but not much more than that. It may be an icy volcanic planet with a subsurface ocean, like we find on Europa and Enceladus in our own solar system. Life on Earth is believed by some to have formed near deep sea vents, and the same process could happen on 1e. No matter where on TRAPPIST-1e water may be, life is possible. There's an energy source and potentially an atmosphere that provides the building blocks for life. But there is one issue. Although all these things are possible, scientists can't completely rule out the possibility that TRAPPIST-1e is a cold, barren, and airless marble with no atmosphere at all. So we need to talk about what could prevent a stable atmosphere from ever forming. And in this case, it's the red dwarf star TRAPPIST-1 itself. I know I said earlier that TRAPPIST-1 was not as bad as other red dwarf stars, but that's not a high bar. Let's take a closer look at this star. Imagine standing with me on TRAPPIST-1e just for a second. Look up. The star above us would appear more than 4 times as large as our sun in the sky. The star would be a deep red-orange color, illuminating the sky as if it were in perpetual sunset. What a sight that would be. Now, as I said, red dwarfs are extremely active, and they produce more powerful flares than our sun, and more often too. The worst recorded geomagnetic storm to ever hit Earth was the Carrington event in 1859, a greater than 1 in 100 year event. TRAPPIST-1 is believed to release a flare this powerful more than once every 2 days. You'd likely be able to watch solar flares arcing out into space in real time, and they carry huge amounts of energy towards a planet, enough that over time any atmosphere could be stripped away, making life as we know it all but impossible. That's assuming that the atmosphere was ever allowed to form at all. As mentioned, red dwarfs are stupendously long-lived. TRAPPIST-1 is expected to exist for 10 trillion more years. That is 700 times the current age of the universe. By comparison, our sun likely only has 5 billion years left before it becomes a red giant. You might think, given the stability and lifespan of a red dwarf, there would be plenty of time for life to find a way, but because of their long lives, their chaotic and energetic teenage years before red dwarf stars settle down are correspondingly longer. It's during these formative years that some planets begin to produce their own atmosphere, slowly replacing their primordial hydrogen-helium atmosphere with one comprised of heavier molecular gases such as carbon dioxide, nitrogen, and methane. These chemicals are released from inside the planet through volcanic activity. The problem is, if the aggressive atmosphere stripping phase of a star lasts too long, then an Earth-sized planet might not have enough resources within its interior to fully generate a stable, life-supporting secondary atmosphere. The unfortunate reality is that if a planet's atmosphere isn't established before 5 billion years, it may never generate one, condemning the planet to a death sentence before it was ever allowed to live. I know it's actually sounding rather hopeless for TRAPPIST-1e, and I bet you're wondering, how is this one of the most promising planets? But we don't yet know one way or the other whether an atmosphere has survived or not. We've already seen there are hints of its existence, and although the star's violent outbursts may be 1e's downfall, they may also be completely necessary for life to begin. UV radiation from flares may be essential to create RNA building blocks, molecules that are central to the metabolism of every life form ever found. And now that TRAPPIST-1 is in its calmer main sequence phase, with lower UV and X-ray irradiation than in its juvenile past, there is a chance of a stable, habitable atmosphere existing on TRAPPIST-1e. And that atmosphere could have protection from the continuing flares with its own magnetic field, just like the Earth does. The Earth's magnetic field exists because its outer core is a moving mass of molten iron and nickel. There is a good chance that TRAPPIST-1e has a similar system. In fact, TRAPPIST-1e's close orbit to the red dwarf could actually help maintain its magnetic field. If TRAPPIST-1e's orbit is eccentric, this would cause repeated compression and relaxation of the planet's shape. This process creates internal friction that could heat the interior as much as 0.18 watts per meter squared. That's roughly 24 times the tidal heating flux generated in the Earth. We see a similar process in Jupiter's moon, Io. Io is tidally locked with an eccentric orbit and gets stretched and squashed by the gravitational interactions with the other Jovian moons, pumping it full of energy and making it the most volcanically active body in the solar system. So, where does this leave us? Well, we may have an Earth-sized, volcanically active, rocky planet with the building blocks for life, its own atmosphere and magnetic field, orbiting in the habitable zone of a relatively calm red dwarf. Or it could be a cold, dead world. So let us know in the comments which you think will eventually be confirmed. We might not get an answer until the proposed Habitable Worlds Observatory, a telescope designed to look for life around stars like our own, which launches in 2041. But until then, James Webb's observations are our best bet. The fact we are able to measure the light absorbed by a thin gaseous layer around a rocky planet orbiting a dim red dwarf star 40 light years away is pretty incredible. And scientists haven't given up hope. They've learned from the first sets of James Webb data and modified their technique to achieve more precise measurements. And as they examine the results of more Webb data, they hope to be able to confirm the presence or absence of carbon dioxide and a secondary atmosphere, a key step in the search for life on 1e. No joy on that front yet though. The most recent study on the topic tentatively suggests that TRAPPIST-1e might have a methane atmosphere, but this might also be interference from its host star, methane in TRAPPIST-1 itself getting in the way of the smaller planet. Perhaps TRAPPIST-1e and its neighbours will turn out to have a unique, inhospitable atmosphere, or perhaps one that could theoretically support life. Or maybe, just maybe, we'll find one just like home. It's exciting to find so much potential for life relatively nearby, even in the midst of an extreme environment. But whatever the atmosphere turns out to be on TRAPPIST-1e, with the recent discovery of formations on Mars that are thought to have been impossible to form without life, I find it hard to shake the feeling that the discovery of extraterrestrial life feels inevitable. The only question is, when? The Astrum newsletter is one of the most beautiful reads you'll ever get. Even if you're not in it for the news, our photo of the week always makes it worth opening. Sign up with the link below. It's a quick, inspiring way to stay connected to everything happening in the cosmos, from discoveries to missions and the stories behind them. Each issue is carefully designed and written to make science feel exciting and easy to follow. If you already enjoy our videos, you'll love having this in your inbox every week. Join thousands of readers exploring space with Astrum.